This video is an introduction to mathematical induction. I found that a lot of students struggle with the idea of mathematical induction. So in this video, what I'm going to do is explain how it works and then use a really easy example to put it into practice. So let's start off by thinking about what we might want to be doing. Mathematical induction is used to prove a statement, which is usually a statement that holds for many values of n. For example, some statement that holds for all n bigger than or equal to 1. So let's think of that as our main goal. Our goal is to prove S sub n, which is just going to represent our statement, S for statement, for all n bigger than or equal to 1. Okay, so before we get into how to actually do a proof by induction, let's think about a few things. I'm going to write down some statements that I claim I have already proven to you, and I want to see if you're convinced that the statement will always hold. So let's start with the first thing. S1 is true. If I prove to you that S1 is true, you're only going to be convinced that the statement is true when n equals 1. Fair enough, because that's all I've shown. If S1 is true, then S2 is true. If I'm able to prove to you that if S1 is true, then it must follow that S2 is true, you're going to say, okay, hold on. I know that you've shown me if S1 is true, then S2 is true, but you also showed me that S1 was true. So you can conclude that you know S2 is also true, and you'd be happy. So far, you're happy that the statement holds for n equals 1 and for n equals 2. Let's see what else I tell you. If S2 is true, then S3 is true. So let's say now I'm able to prove to you that if S2 is true, then S3 has to be true. Well, from the previous step, you already knew that S2 was true, so you would conclude happily that S3 is also true. And I can continue like this. If S3 is true, then S4 is true. Again, if I prove to you that if S3 is true, then S4 is true, you're going to conclude that S4 is also true, because we started off knowing that S1 was true, and we used a domino effect to say, okay, that means S2 is true, then S3 is true, now S4 is true. But this looks like a lot of work. I have to keep going, and I have to again prove to you that if S4 is true, then S5 is true. And then once I've done that, I have to again prove to you that if S5 is true, then S6 is true. That's too much work. So what we want to do is cut down all that work and do all of that in only one step. And that's the beauty of mathematical induction. So instead of doing this many times, in fact, we'd have to keep on going to infinity, what we're going to do is replace this entire block by a single statement. If Sk is true for some k bigger than or equal to 1, then Sk plus 1 is true. Isn't that great? I can do this once. If I prove to you this statement in red, if Sk is true for some k, then Sk plus 1 must be true. What you get from that one statement is all of these statements. So let's say I only prove two things for you. First, I prove that S1 is true. You're happy that the statement is true just for n equals 1. And then I prove to you this statement in red. If Sk is true for some k, then Sk plus 1 is true. Will you be satisfied that it has to be true for all n? Let's think about it. You are already satisfied that it's true for n equals 1. When you think about n equals 2, you say, well, okay, all I have to do is say it was true for k equal to 1. So now I know by the red statement that it's true for k plus 1, which is 2. And again, you loop in. You say, now I know it's true for 2, so it must be true for 3. And you keep going, and it's true for all n bigger than or equal to 1. So if that makes sense, let's do an example. Remember our goal. Our goal is to be able to prove two things. The first thing is this piece, and the second thing is this piece. So what I'm going to do is write down those two pieces to remind us of what we need to do. So let's recap. If I'm going to prove to you that the statement S sub n is true for all n bigger than or equal to 1, then I have to do two things. The first thing is to show that it's true for the first value of n, in this case, n equal to 1. The second thing that I need to do is to prove to you that if the statement is true for some value n equal to k, then it must also be true for the next value, n equal to k plus 1. So those are the two things that I need to accomplish. This first one is called the basis. This second one is actually the trickier part, and that's called the inductive step. So to show you how this works in practice, I've chosen a really easy example so that if this is the first time you've seen mathematical induction, it should be really clear. Prove that 3 to the power of n minus 1 is even for all n bigger than or equal to 1. The reason I've chosen this example is because it's pretty clear that 3 to the power of n minus 1 is going to be even. So you don't even really need mathematical induction to do this. You can use other methods. But mathematical induction can be used, and it's very straightforward. So let's work through the steps together. Step number 1 is we need to prove the statement is true for n equal to 1. What is the statement? The statement is that 3 to the power of n minus 1 is even. That's our statement, Sn. So if we want to show that this is true for n equal to 1, what do we have to do? Plug in n equal 1. The basis is 3 to the power of 1 minus 1. Is that going to be even? It equals 2, so yes, S1 is true. The basis is usually the easy case. The harder case is to prove step 2, the inductive step. So what are we going to do? In order to prove the sentence here given in part 2, what we have to do is suppose that the statement is true for some value of k. So that's going to be our assumption. The assumption is called the inductive hypothesis. We are going to suppose that Sk is true for some k bigger than or equal to 1. What we now need to do is to prove that Sk plus 1 is true. Well, let's think about this for a moment. If we know that Sk is true, let's figure out what that means in terms of our actual statement in this example. 3 to the power of k minus 1 is even. Don't forget that this is for some k. Now what do we need to do? We need to take a look at the statement for k plus 1 and prove that that is also true. So we want to look at 3 to the power of k plus 1 minus 1 and show that that's even. Let's do that. Now, 3 to the power of k plus 1 minus 1. What are we going to do with this? We're somehow going to want to use our inductive hypothesis. That's going to be key here. We're going to want to use the fact that 3 to the power of k, then minus 1, is even. We're going to want to use that fact. So how do we do that? I see that there's a 3 to the power of k plus 1, which is very similar to 3 to the power of k. I'm just going to factor out a 3. So I now have 3 times 3 to the k minus 1. So far, I'm not quite there, but what I do know is that 3 is 2 plus 1. So I'm just going to replace this 3 here with a 2 plus 1. And I still have 3 to the k, and I still have a minus 1. And now let's take a look at what I have. I have 2 times 3 to the k plus 3 to the k, because I have 1 times 3 to the k, minus 1. And this is the point in which I'm almost finished. Take a look at this piece right here. 2 times 3 to the k is clearly even because of the factor of 2. Let's look at the other piece. 3 to the k minus 1, how do we know that's even? We know it's even because of our inductive hypothesis. So we have an even number plus an even number, which is clearly even. In other words, we've just shown that 3 to the power of k plus 1 and then minus 1 is also even. So let's recap. We were able to show that the statement was true when n equals 1. Then we said, let's suppose it's true for some value k. So we took that assumption. And using that assumption, we were able to prove that it must then be true for the value k plus 1. In other words, we accomplished both of our tasks. We proved that it's true for the first value of n, the basis, and then we proved the inductive step. We proved that if it's true for some value k, then it's true for the next value of k. And so we conclude that by the principle of mathematical induction, it's true for all values bigger than or equal to 1. Remember that it doesn't have to start at n equal 1. You might have a statement that you're trying to prove for n bigger than or equal to 6, and then you start with a basis of n equal to 6. So the tricky bit is usually figuring out what to do after you've made the inductive hypothesis. So here, when we made the inductive hypothesis in red, this part right below was the tricky bit. Now for this example, it wasn't that tricky. But whatever type of mathematics you're doing, that's the part that's usually a bit more involved. So I hope this made sense, and now you understand the principle of mathematical induction. See you next time. Why that is true. So let's say you have 3 pigeons.